Welcome to this explainer. Today, we're going to break down exactly how you can build a local, highly secure AI application without relying on any external APIs. So, if you've ever wanted to build your own intelligent system that can securely query your private documents and do it entirely on your own hardware, well, you're absolutely in the right place. Right off the bat, let's talk about the Achilles heel of large language models. They're frozen in time, and they have this really bad habit of just making things up when they don't know the answer. You ask a foundational model a highly specific question about your company's internal data, and it tries to guess based on its training weights. That's exactly what leads to those confident yet completely wild hallucinations we've all experienced. The incredibly elegant solution to this is RAG, or Retrieval-Augmented Generation. You can basically think of it as an open book test for your AI. Instead of forcing the model to memorize every single fact in the universe, we give it a live, updatable memory to pull verifiable facts from, exactly when it needs to generate an answer. And the shift in thinking here is pretty profound. RAG essentially takes the burden of knowledge off the model's frozen parametric memory, those billions of internal weights it learned during training, and shifts it to a non-parametric document base. It's a total game changer because you don't have to retrain your massive model every time a new document drops. You just update your text files. Okay, here's our quick roadmap for today. We're covering the RAG concept, the developer toolkit, chunking and embedding, the vector database, building the LLM pipeline, and finally, testing the RAG chain. Part 1. The RAG concept. Let's take a quick high-level look at how this architecture processes a query on the fly. Literally, every RAG system goes through these 4 specific stages to turn your prompt into a grounded answer. First up, the user's query gets encoded into a vector. Second, we search our document index to pull the most relevant text. Third, we prep that context, usually just by appending it onto the original prompt. And fourth, the generation stage, where the LLM reads it all and actually talks back to you. Moving right along to part 2, the developer toolkit. Let's look at the exact stack you need to pull this off. So our local stack is actually really specific. Python is obviously our foundation. LangChain is the orchestrator tying it all together. For the vector database, we're using FAISS. That's Facebook AI Similarity Search, which is just stupidly fast. And we're grabbing our embedding and generation models straight from Hugging Face. The best part? Everything runs locally. Literally 0 data leaves your machine. Part 3, chunking and embedding. This is absolutely crucial. Before our AI can actually read anything, we have to break our documents down into bite-sized pieces. Because here's the thing, critical facts are often scattered across totally different documents, which makes chunking vital for keeping the context intact. For example, say you ask about a specific Champions League final. One chunk might mention the location, Lisbon, while a totally different chunk, buried in another file, has the winner, Bayern Munich. If you don't chunk your data smartly, the retriever grabs the location, misses the winner, and your LLM is flying completely blind. So let's look at the actual code and see how we build this step by step. It starts with loading our data and turning it into high-dimensional vectors. We load the text, we split it up, and then we apply a Hugging Face model, specifically all mini-LM L6v2, to embed those chunks into numbers. To do that, we use LangChain's character text splitter. A chunk size of 500 characters is a pretty solid baseline, but the real secret sauce is that 100-character overlap. We do that intentionally so that the semantic context doesn't just fall off a cliff at the boundaries. Think of that overlap as a safety net. It guarantees a key sentence isn't sliced directly in half, giving our model the complete, coherent thought it needs. Part 4, the vector database. This is how we get that lightning-fast retrieval once everything is chunked and embedding. FAISS is basically acting as our non-parametric memory bank. Since our chunks are now vectors floating in a high-dimensional space, FAISS uses approximate nearest neighbor techniques to hunt down semantically relevant chunks in, milliseconds. When you ask a question, FAISS just compares the math of your question to the math of the document chunks and spits out the closest matches. And setting this up in Python, it is astonishingly simple. 2 lines of code. With FAISS.FromDocuments, we load the chunks and the mini-LM model right into the store. Then, we just expose it as a retriever. That retriever object is exactly what LangChain queries in the next step, linking the database right into our logic flow. All right, part 5, building the LLM pipeline. This is where we orchestrate the generation so the LLM can actually formulate a real response. We configure Hugging Face to use GPT-2 for our generation. Now, notice we set device equals 0. That's for GPU acceleration, which speeds up inference massively if you've got a local graphics card. We're also capping max new tokens at 200. You want to do this to keep memory usage from blowing up, and it forces the application to give you concise answers instead of just rambling on forever. Now this prompt template, this is the strict rulebook for our AI. We are explicitly telling the model, answer the following question based on the provided context. We pass the retrieved chunks into that context variable and the user's question into the query variable. It literally forces the LLM to ground its response entirely on the injected text, totally bypassing its internal hallucination-prone memory. And here is where LangChain really flexes its muscles. We create an LLM chain to handle the prompt formatting, and then we wrap the whole shebang in a retrieval QA chain. This master chain automates the entire flow. User query comes in, FAISS retrieves the docs, the prompt is formatted, and the LLM generates the final answer. Seamless. Finally, part 6, testing the RAG chain. We need to handle edge cases, so our pipeline doesn't just crash under pressure. We throw in this really simple supporting function to aggressively truncate our inputs. Think about it. If our retriever accidentally pulls way too many overlapping chunks, we could easily blow right past the LLM's token limit and the whole app crashes. This function just ensures our context stays strictly within safe boundaries before the generator even sees it. As you go off and test this yourself, keep this rule of thumb in mind. A bad answer isn't always the LLM's fault. If the output is garbage, check the retrieval. Did the database even return the right chunks? You really need to experiment with your chunk sizes. And hey, if you scale this into production, seriously consider hybrid search. Mixing this dense vector similarity with a traditional sparse keyword search is a fantastic way to bulletproof your accuracy. By keeping the knowledge storage inside a local vector database, we've essentially built a highly secure, incredibly efficient AI system right on our own desk. But it does leave us with a pretty wild question about where AI architecture is heading. Are foundational models just going to become these hyper-efficient, lightweight reasoning engines that totally rely on external RAG systems for facts? It's definitely something to chew on. Thanks for joining this explainer. Now go build something awesome.